Xraster is a QGIS plugin designed for scientists and specialists to analyze multidimensional data available in the NetCDF format, which describes marine environments and climate. Built on the Python Xarray library, Xraster provides an interface to this module within a GIS environment, enabling the entire data processing and analysis workflow without requiring programming. In this video, using Xraster, we will try to answer the question of what happened in the Gulf of Gdańsk over the course of a year, focusing on ice phenomena, water temperature, and salinity. The Gulf of Gdańsk is located in the southeastern part of the Baltic Sea with an average depth of around 50 meters and a maximum depth of 118 meters. The western part of the Gulf is formed by the shallow waters of the Bay of Puck, while the southeastern part is the Vistula Lagoon, separated by the Vistula Spit and connected to the open sea through the Strait of Baltiisk. In winter, ice phenomena occur in the sheltered waters of the Gulf. The outflow of the Vistula River, the ninth longest in Europe, plays a significant role in the region's hydrology, with its mouth located on the Gulf shore. To obtain the necessary data, we go to the Copernicus Marine Data Store. We need to log in, and for first-time users, register. We find the product called Baltic Sea Analysis and Forecast. We select it and proceed to data access. To download data, we'll choose the simplest method. Click here. This product contains several datasets. We select the dataset with daily averages across various variables. We choose variables, sea ice concentration, salinity, and temperature. Next, we define the area of interest by setting the window size, which will be used to extract data for the Gulf area. We'll analyze the past year. Since today is October 31st, our data will cover the period from November 1st of last year to the present day. We'll specify a depth range from the surface to 110 meters. Now we can download the data. We go to QGIS and open Xraster by clicking on the program icon. Then we open the Data tab. We input the downloaded data and click OK. A data description appears in the panel. The data has 4 dimensions: a plane defined by geographic coordinates, latitude and longitude, 28 depth levels, and 366 time points. As expected, these represent consecutive days. We can check the ranges of these values below. At the end of the description, the 3 variables we entered are listed: ice concentration, salinity, and water temperature. Units are shown next to each variable name. For example, temperature is in degrees Celsius. Additionally, we can apply a mask to define zones that may be treated as areas of interest. The mask can be displayed by clicking the Plot Mask button. It designates 4 zones with integer values. The inner and outer areas of Puck Bay are marked by numbers 1 and 2, the Vistula Lagoon by 3, and the open waters of the Gulf by 4. Other areas are assigned a value of 0. This mask will allow us to analyze selected areas. The mask, labeled as mask, is added to the coordinates with a range from 0 to 4. To begin the data analysis, we go to the Subset tab. We need to specify the subset variable. We select ice concentration and click OK. Start a message appears. Selection successful, with the numbers 3, 1, 1. The number 3 represents the number of dimensions for the variable. Since ice concentration only applies to the surface, even though the dataset has 4 dimensions, this variable will have 3 dimensions, meaning a 2-dimensional sea surface and time. The numbers 3 and 1 indicate the data type as a slice of space and time. The final 1 signals the presence of a mask. We go to the Figures tab. This type of data will be visualized with a histogram. We click Plot. We can zoom in on part of the figure and observe that there was ice cover during this period. We will create a map of maximum ice cover. Ice concentration ranges from 0 to 1. For each cell, we will determine the highest value over the course of the year. This will show us where ice was present at any point. We go to the Statistics tab, select the maximum statistic, and click the Plot button. We see that the entire Vistula Lagoon was covered by ice, as well as parts of the inner Puck Bay. Now, we would like to find out how long the ice cover lasted in both areas. We will use the sum of the concentration. For example, if the concentration is 0.5 for 2 days, we will get the equivalent of 1 full day of continuous ice cover at that location. We select sum as the statistic and press plot to generate the next figure. We see that in the Vistula Lagoon area, the ice cover lasted for about a month, while in Puck Bay, it was much shorter, lasting a maximum of around 2 weeks. Now we still need to find out when the ice cover occurred. We'll create a time series plot showing changes in its concentration at a selected point. We'll choose a point and record its coordinates. By moving the cursor, we can see the coordinates and the number of days. We now need to generate a new subset at this point. We go to the Subset tab and enter the coordinates. Additionally, we will limit the time to the beginning of May. We press the OK button. The data type is 3, 3, which indicates a point in space and a time slice. We go to the Figures tab. This type of data gives us a time series, so we click Plot. We see that the ice cover occurred twice. The first time was from the beginning of December to December 23rd, and it began again in early January, dissipating by the end of that month. The created maps can be saved as images or exported to QGIS as raster layers. The data from the time series can be exported to a text file. We will now close the figures and proceed to further analysis. Now we will analyze the flow of water from the Vistula River across the surface of the Gulf. We'll try to see the scale this phenomenon can reach. We select the variable SO representing salinity, set the depth to 0, and click OK. We get a subset of type 4, 11, meaning a slice of space and time for a single depth. We then go to the Figures tab. We display the histogram by clicking Plot. We see that surface salinity in the Gulf ranges from 0 to 9 PSU. Now let's look at a map of minimum salinity for the entire Gulf. We go to the Statistics tab, select Minimum as the statistic, and click Plot. Our map shows the maximum spread of Vistula River water. Using the cursor, we can examine this map and see that even far from the mouth, salinity values may not exceed 2 PSU. To get the salinity distribution for a specific day with a strong spread of Vistula waters, we'll create a time series of salinity values at a selected point. Then we'll look for days with minimum salinity values. We record the coordinates of this point and return to the Subset tab. We enter the point's coordinates and the full time range, which can be done in a simplified way. We press OK. The subset type is now 4, 3, which means point in space, single depth, and time slice. We go to the Figures tab. We see that for this subset, we get a time series. We click Plot. This shows how the surface water salinity changes at the selected point. We look for the dates with the lowest values, using zoom on our plot. We see that the lowest value occurred on February 26. We return to the Subset tab, use Reset to restore the default settings, then set the depth to 0 and the date to February 26. We click OK and go back to the Figures tab. We click Plot and obtain one of the maximum spreads of Vistula waters throughout the year. We can examine how salinity changed along and across the outflow using the cursor. We can also observe low salinity values in the area of the Vistula Lagoon. Let's check the vertical salinity profile for that day at the previously determined point. We return to the Subset tab. We enter the coordinates of the point again, keep the date, and input the full depth range. We click OK. The subset type is 4, 44, which means point in space with a slice of depth at a single time. We go to the Figures tab. This time, the data create a vertical profile. We click Plot. we see that the layer of freshwater is characterized by a very strong gradient and extends down to a depth of 7 meters. On the previous map, the distinctly lower salinity in the Vistula Lagoon is clearly visible. We will examine how the average salinity at the water surface in the lagoon changes from month to month. We return to the Subset tab. We click the settings to reset. In the mask, the Vistula Lagoon is designated with the value 3. We enter the filter as wherever.mask equals 3, set the depth to 0, and press OK. We go to the Group by Time tab. We will group the values by month using the mean statistic. We click Run. Then we go to the lower part of the tab and click Plot. We obtain a graph showing the average salinity values for the lagoon for each month. The lowest value occurred in May, while the highest was in November. We will conclude the salinity analysis here, close the windows, and return to the Subset tab, where we will focus on analyzing water temperature. We will begin the water temperature analysis by creating a median map of surface temperature for the summer period. We select the variable temperature, set the depth to 0, and limit the subset to July and August. Using months instead of a continuous time range is particularly useful when analyzing specific months over multiple years. We press OK and proceed to the Statistics section. We set the statistic to median and click the Plot button. The generated map contains the necessary information, but it's not suitable for publication. Saving it by clicking the disk icon will save it in screen resolution. To adjust the map's save parameters, go to the Figures tab, where we can set the font size and the resolution of the image in DPI. The shape of the figure can be adjusted manually as well. Now we'll make changes to the figure. Click on the second to last icon, select the first option, and modify the map's title and axis labels as needed. We go to the second tab and change the color bar to Jet. We click the Edit Figure icon again and select Color Bar. Here we change only the vertical axis label to Temperature and press OK. To save the figure, we first go to Save Plot File and enter the figure's name. We complete the process by clicking the Save Plot button. In the directory, we locate the saved figure and display it. We can see that the resolution of the figure has been appropriately increased. We close the windows and return to Data. We display the mask. Our goal is to determine the average temperature of the entire water mass in the Bay of Puck area for July and August. In the mask, this area is marked with the identifier THOD1. We go to Subset and enter the months 7, 8, July, and August. To also view a histogram, we apply a mask filter for the Bay of Puck. We press OK and go to Figures. Using the plot function, we display the histogram of our data. We proceed to Statistics. We will use zonal statistics. We enter the Zone 1 and specify the file name. We click Run. We navigate to the generated file, which is a text file containing statistics calculated for each day in July and August. The average value can be computed from the mean column in another program. Next, we return to the average value map. We will now analyze how the temperature in the water column changed throughout the year. We select a point and record its coordinates. We go to Subset. We enter the coordinates, leaving the other fields empty. We press OK and move to Figures. For this type of data, a depth-time cross-section figure will be created. We click Plot. The generated figure shows how the temperature in the water column changed day by day. Using the cursor, we can explore the figure by reading the time and temperature values. Xraster allows for various analytical approaches, enabling us to perform a range of custom tasks. Our goal now is to create a map of the number of days with a daily average surface water temperature above 22 degrees Celsius. To accomplish this task, we need to find a way to utilize the capabilities offered by Xraster. We will go to Subset. In the first step, we will create a subset of the data at the surface, including only values greater than or equal to 22 degrees Celsius. The spatial structure will remain unchanged, but temperatures with lower values will be replaced with no data. We enter the surface and the condition in the form of where var equal 22. We click OK and go to Figures, where we create a histogram by clicking Plot. We can see that such temperatures occurred. The goal will be to convert these values to 1 for later summation. Therefore, we need to perform the subset transformation again. But first, we have to save it as a new NetCDF dataset. We go to the Clip Join tab and use the option Save Current Selection from Subset. We enter a name and click Save. We go to Data and import the created dataset. We click OK. The dataset creates an identical plane, but it is limited to the surface and contains only the temperature variable. It is now a three-dimensional dataset. We go to Subset. To change the variable values to 1, we need to understand how the calculate function works. It modifies the value of the selected variable, and in the field, we enter the rest of the expression that modifies it. If we do not enter anything, the program will append an expression equivalent to multiplying the variable by 1, meaning it will simply multiply it by 1. Since we want to change all variables that are not no data to 1, we will multiply the variable by 0 and then add 1. We click OK and go to Statistics. We select Sum and click Plot. We obtain a map showing the number of days with temperatures above 22 degrees during the year 2024. The most days with temperatures above 22 degrees occurred in the Vistula Lagoon, with over 30 days. In the open waters of the bay, the values were up to 10 days. In the internal waters of the Bay of Puck, there were a maximum of 7 such days. This analysis concludes the presentation. We aim to demonstrate how Xraster can be utilized for monitoring the current state of the coastal zone environment, showcasing as many capabilities of the program as possible. The plugin was developed in the Data and IT Department of the Institute of Oceanology, Polish Academy of Sciences, by Jacek Urbański. It can be downloaded from the website, where you'll also find a user guide and links to instructional videos. Please direct any feedback to the provided email address. This is an early version of the program, so we would appreciate reports of any issues encountered.